Hi everyone, and welcome to another video of this channel. So today we will be investigating a very interesting circles problem from an old Purple Comet High School math meet. So let's get started. So basically we have this black line, right? And we have this circle, and this line is tangent to the circle, and the circle has radius A. And we also have this small circle R1. It's tangent to this big red circle and this black line. And then we also have a circle whose radius is R2. And it is tangent to this blue circle R1 right here, this red circle, and this line. We can also construct such a circle here, and in fact we can construct like an infinite chain of circles that goes from R1 and to the left, but our chain will go to the right. And of course we are assuming that R sub 1 is less than A. And so this circle is less than this circle. And then we want to ask how many circles are in the sequence. In other words, after how many circles will we not be able to construct another circle? So suppose there are n circles in the sequence, right? And now I will state a fact that is intuitively clear, which is that R sub n is bigger than or equal to A. So once again, there are n circles in the sequence. The last circle in the sequence has radius R sub n. Why? Well, if the last circle in the sequence is bigger than A, right, let's suppose like it's some sort of circle like this, then R sub n plus 1 will be tangent to this line to the left of this circle A. And so that is what makes this circle R sub n the last circle. That the fact that the circle R sub n plus 1 will be tangent to this line to the left of this circle A. But we also want to make this clear that we want the least such n, right? So, for instance, we don't want this circle right here again, right? Because this circle's radius will also be larger than A, but it's not it's not even in our sequence. So we want the least such n. And so now, basically, our strategy is try to express R sub n in terms of n. And now we will investigate a very interesting fact about circles that is useful in general, and that will be crucial to help us solve the problem. So we have these three circles, right, that are tangent to this line right here. And they're also tangent to each other, so we can connect their centers like this. And they have radii x, y, and z. So now we aim, our goal is to express z in terms of x and y. And so basically we draw this dashed line right here. And it's the altitude from here, from this center of the orange circle to this radius right here. And this side right here, that's z. And then the leftover of this radius is x minus z. But then this segment right here, right, this green segment, this is x, and this right here, this orange segment, that's z. And after just using the Pythagorean theorem, we get that this side is equal to the square root of x plus z squared, right? That's the hypotenuse squared, minus the other leg squared, that's x minus z squared. And then we just do some simplifications and get that this is 2 times the square root of xz. Okay, so now we do the same exact drill on this side right here. We also draw the altitude. This side right here is z, this one right here. Then this leftover is y minus z. And then this segment is z, this one is y. And after using the Pythagorean theorem only inverted, we get that this new dashed line is 2 times the square root of yz, right? We just do some simplifications. And now we can do the same exact thing for this one right here. So we can also draw this altitude, right? And this one right here, so this side right here, right, that's length x minus y, because this side right here is y, this side right here is x. And this side right here, right, this hypotenuse, that's x plus y. And so we get that this new long dashed line is equal to, also after some simplifications and using the Pythagorean theorem, 2 times the square root of xy. But now notice that since this resulting shape right here is a rectangle, this side right here is equal to the sum of these two sides, and we get that 2 times the square root of xy equals 2 times the square root of xz plus 2 times the square root of yz. And now dividing both sides by 2 and dividing both sides by the square root of xyz, we get that the 1 over the square root of z is equal to 1 over the square root of y plus 1 over the square root of x. And so this is like a really important identity that is definitely worth remembering and is true for circles in general. But this thing can certainly be applied to our problem, right? We can notice that we can replace x with a, y with r2, and z with r1. And so we get, right, that 1 over the square root of r2 plus 1 over the square root of a is equal to 1 over the square root of r sub 1, which simplifies just like this. And now, right, if we think about the next circle in the sequence, R3, we get a very similar expression with A, R3, and R2. Just like this. But now we can substitute this expression for R2 into here. And we get that 1 over the square root of R3 is equal to 1 over the square root of R1 minus 2 times the square root of A. And from here, it's just basically, really, it looks a lot like the arithmetic sequence, right? So it's kind of this domino effect. And just by noticing some patterns here, we get that 1 over the square root of r sub n is equal to 1 over the square root of r sub 1 minus the quantity n minus 1 over the square root of a. But notice, right, from our original observation, from our intuition, that r sub n is bigger than or equal to a. So then just taking the square root of both sides of this inequality and dividing both sides of this inequality by 1, remember the inequality sign flips, right, when we reciprocate both sides. We get this right here. So now we can combine this one with this one right here. And we get that 1 over the square root of a is less than or equal to 1 over the square root of r sub 1 minus n minus 1 all over the square root of a. And now, after some simplifications, we get that n is bigger than or equal to the square root of a over r sub 1. But then also remember how we added this right here. We want the least such n, right? And so the least n, right, of course, that's an integer, right, because n is the number of circles, right? N is the number of circles in the sequence. Any like number of circles always has to be a positive integer, right? We also know that n is the least such integer, and so we get that n is equal to the ceiling function of the square root of a over r sub 1, where a over r sub 1 is inside the square root. And so we're done. That is the answer to our question. So I'm just going to demonstrate this question, this like problem, the solution on a quick example. So in the original purple comet test, we had a equals 2008 and r1 equals 1. But we will add a bit of a futuristic tone to this problem, and let's set a equal to 2022 and r1 is equal to 1. So n is equal to 45 in that case, right? Because the ceiling function of the square root of 2022 is 45, right? That's the square root of 2025. And so basically we can just circle the answer and we're done. So now I'm going to give you a brief graphical demonstration of how this how this closed form works right here. Okay, so here I have this little graphical demonstration of our explicit formula. So here I replaced r sub n with f of x, right? I replaced n with x. And then here I have our explicit formula solved for r sub n with our little example with r sub 1 being equal to 1 and a being equal to 2002. So as you can see here, this right here is the graph of all the r sub n values given the x, of course, because we're not doing this in terms of n. And then this branch right here, well, we'll talk about this branch later. So firstly, let's turn our attention to what is happening to the left of this one right here, because notice that when x is equal to 1, right? When x is equal to 1, f of 1 equals 1. That's technically what we initially had, right? But then if we have 0, right, this represents the infinitesimal chain of circles that can be continued to the left of our circle with radius r sub 1. Okay. So now let's look at the different values of r sub n. So, like for instance, when there are 3 circles in the sequence, right, the radius of the third circle is just barely over 1. So it continues like this, and finally crosses the threshold of 2 at a equals 15. So the 15th circle already has a radius that's bigger than 2, but it's still increasing very slowly. Okay, so now it's increasing already. So at a equals 40, our radius is 56, but it's still not quite 2022. Okay. So then in the 43rd circle, we have our radius being approximately equal to 230. Then 44 is 522, and then the 45th circle, it's bigger than 2022, right? That was our original hypothesis. But then, I mean, if we go over this threshold, there's this algebraic thing called the 46th circle. I mean, this 46th circle right here is on this branch right here of this algebraic graph. But this like right branch, right, of this graph is just like an algebraic remainder of our purely geometric calculation. So this right here doesn't really represent anything geometric that has to do with our formula right here. And yeah, so that is just like graphical justification and exploration of our original hypothesis. Okay, so I hope you like this video. Thanks for watching, and I'll see you next time.